Hello everyone, my name is Mengyuan. I'm from the Ohio State University. Today I'm going to present our paper, Cipherleaks, Breaking Constant Time Cryptography on AMD SEV with the Ciphertext side channel. This is a joint work with my advisor, Dr. Zhang from Southern University of Science and Technology, Dr. Huibo Wang, Dr. Kang from Baidu Security, and Dr. Yueqiang Cheng from NIO Security Research. Let's start with some background about AMD Secure Encrypted Virtualization, SEV. So SEV is AMD's new technology since 2016, and it's adopted or will be adopted in all those mainstream cloud service providers. SEV is built at top both traditional virtualization and the hardware memory encryption technology. The goal of SEV is to provide additional protection towards virtual machine VM in cloud. According to SEV's security assumption, it tries to protect SEV-enabled VM even the host is not trusted anymore. Let's look at how SEV achieved this ambition goal. The hardware memory encryption helps SEV-enabled VM to automatically encrypt and decrypt their memory. In AMD system on chip, besides CPU, there's another processor called secure processor, which will manage some AES keys. And there is also a 128-bit AES encryption engine, which is in charge of encryption and decryption on the fly. So data are unencrypted inside the CPU, and when guest VM tries to write data to memory, data will be automatically encrypted. Similarly, when guest VMs reads data from memory to cache, data will be automatically decrypted by the AES engine. Then I will talk about the AES algorithm used by SEV. So because the memory is accessed randomly, memory is independently encrypted per aligned 128-bit block. And to avoid malicious hypervisor inferring the plaintext via the same ciphertext, SEV use exclusive or encrypts exclusive or mode, the XEX mode, to do the encryption. And the additional physical address-based tweak function, TX, is used here. So when the AES engine encrypts the data will first be exclusive OR with the tweak function before the encryption, and after the encryption, it will be exclusive OR with the tweak function again. So since SEV first released in 2016, there are some extensions of SEV. The second generation of SEV is called SEV Encrypted State, SEV-S. SEV-S aims at protecting registered states in VM control block, VMCB. In SEV, when there is a word switch from the guest VM's word to host's word via VM access, the registered states are saved unencrypted in VMCB. Then in SEV-S, the registered states are now saved encrypted in an area called VM save area, the VMSA. The hardware also restricts the hypervisor's write access to VMSA during VM access. The third generation of SEV is called SEV Secure Nested Paging, SEV-SNP, which is released recently. SEV-SNP aims at protecting nested page table and preventing ciphertext modification. SEV-SNP uses a structure called the reverse map table, the RMP table, to maintain the information about the address translation as well as the ownership of memory pages, which helps prevent NPT modification and also restricts hypervisors' write access to VM's memory pages. All existing attacks can be mitigated by SEV-SNP. So that's all about the background. Then let's talk about our paper. This is the outline. I will begin with an unexplored side channel, what we call it Ciphertext side channel. And then I will talk about what Ciphertext side channel can do. I will also show two end-to-end attacks, followed by some discussion and then the conclusion. Okay, the Ciphertext side channel. The Ciphertext side channel targets at continuous monitoring ciphertext inside the VMSA. So when there is a VM access, registered states are encrypted and stored in VMSA. Those registered states are also encrypted per 60-byte block. Usually register stores an 8-byte value, and thus each 60-byte block may contain 2 registers value. However, some 60-byte block may contain only one register value like the ISP, RAX, CR2 in the figure. The rest 8 bytes are reserved. For VMSA, the adversary doesn't have write access but have read access. This is also the fundamental of ciphertext side channel. By forcing VM access and record ciphertext inside the VMSA, the adversary can collect a sequence of ciphertext during VM's execution. That's the ciphertext side channel. Then the question is, what can the adversary get from those ciphertext data? With the help of those ciphertexts, the adversary can first infer VM's execution state. So by continuously monitoring the ciphertext change, the adversary can infer VM's different activities. For example, when the block containing CR3 and the CR0 changes, the adversary can learn there is a context switch. And since CR0 barely changes, the ciphertext of this block can also use as ID of different processes. The adversary can also learn an IP at once the IX changes and so on. By combining those very interesting information with controlled channel and nested page fault information, the adversary can identify execution state for a known binary. The adversary can also use the ciphertext side channel to recover some registers plaintext. And this will make the ciphertext side channel become more powerful if the adversary can build a ciphertext and plaintext dictionary. So one way to collect that dictionary is via non-automatic VM access, the NAE event. The NAE events are those events that need to involve exposing some register's state to the hypervisor. For example, the CPU ID emulation. When there is a CPU ID instruction, a VMM communication exception, the VC exception, is generated by hardware. And the VC handler inside the guest VM is going to handle it. The VC handler will copy necessary register state to an unencrypted area called guest host communication block, the GHCB. And then the VC handler triggers a VM access. The hypervisor needs to emulate the CPU ID instruction. And at this time point, the adversary can learn the plaintext of RAX and RCX from GHCB. For the sequential VM run, the VM will resume from VC handler. The adversary can learn the corresponding ciphertext when the guest VM enters the VC handler or access the VC handler. In this way, the adversary can build a ciphertext and plaintext dictionary. For RAX, the adversary can collect all ciphertext and plaintext pair when the plaintext ranges from 0 to 127 by those NAE events during the boot period. Okay, after introduce the attack primitives, I will show two end-to-end attacks. The first attack is about stealing RSA private key from SEV-enabled VM. Here we target at the list OpenSSL library. Specifically, we target at a function called big number get bits 5 inside the function bn modulus exponent constant time. So the bn get bits 5 will get 5 bits from the private key each time. It will put the result in RAX and then return. The adversary targets at the ciphertext of RAX and use the following steps to steal the private key. So the adversary first use execution state inference method we introduced before to locate the guest physical address of two key functions. Function 1 is big number get bits 5, and the function 2 is big number power 5. The adversary then unsets the present bit of function 1 and function 2, like unset function 2's present bit when intercept function 1's nested page faults. So because of the while loop, the adversary can see total 410 iterations of nested page faults of both function 1 and function 2 for 2048-bit RSA private key. The adversary can then get the IX ciphertext when intercept the function 2's nested page fault, which is also the time point when bn get bits 5 finish execution and is going to return. Each time the ciphertext represents 5 bits of the private key. The adversary then compare the ciphertext with the dictionary and recover the plaintext of the 5-bit private key each run. So after the total 410 runs, the adversary can collect the entire private key with 100% accuracy. Okay, then a quick example about breaking ECDSA. So it's quite similar. This time the adversary tries to steal the nonce k in ECDSA and targets at a function called big number is bit set, which will return 1 if certain bit is set and return 0 if it's unset. The adversary follows a similar steps. First, determine the guessed physical address of the two key functions, and then unset the present bits and get the IX ciphertext at the right time point. In this case, since the IX stores either 0 or 1, the adversary can directly infer the nonce k with only 1 bit entropy. It can also look up with the dictionary, and in this example, the adversary can also recover the plaintext of nonce k with 100% accuracy. Okay, that's two end-to-end attacks. A quick discussion. So in our Cipherleaks attacks, we collect the ciphertext side channel in page level, which means we only collect the ciphertext when there is a page fault. The adversary can also use APIC interrupt to get instruction level ciphertext side channel, which can infer the execution states inside the same instruction page. I also want to discuss the hardware fix. There are two potential hardware fixes. One is to restrict software level read access to VM's memory as well as the VMSA with the help of the RMT table. The other hardware fix is to add randomization when stored registers in VMSA. According to our discussion with AMD team, there might be a hardware patch soon in the future. Okay, finally, the conclusion. So it is the first explosion of a novel ciphertext side channel on AMD processors, and we present the Cipherleaks attacks and show two end-to-end attacks against the constant time ISA and the ECDSA implementation with 100% accuracy. It's also the first known attack against SEV-SNP, and AMD will announce a security bulletin and assign a CVE for Cipherleaks. We also discussed some hardware countermeasures. Okay, that's all. Any questions? You can also reach me or my advisor with our email address. Thank you all for listening.